Okay, so let's start. Okay, so before we start, just to remind you, so projects are due, status reports are due end of next week, which is the 14th. There was a typo, I think it said 16 on the web page, so it's now fixed. Also to remind you that the final exam is planned to be in class, the last lecture, which is December 9. It's almost there. We're almost there. So, okay. Questions on this? Yeah. I think I didn't put it on the web. I think it's supposed to be the day of the final, which is something like a week after this day. 16, I think, yeah. But I'll check that it's on the 16 plus or minus 1. I think that's the right day, yeah. Yeah. I can't hear you. It's a Friday? Okay, if it's a Friday, then it should be the 8th. I want it to be the end of Thursday. So no, I'm talking about the 14th of November. Is there any agreement what day of the week is it? It's a Friday. Okay, so it will be 13 then, to make it a Thursday. So let's change it. Okay. Any other questions on this? Okay, so just one note. Next lecture on Thursday, we're going to deviate from what we are doing now and talk a little bit about the practice of machine learning, give some examples of how to build models with existing software. And let's talk about where we are. So we started to talk about Bayesian learning. Basically, as I said, it's everything we're talking about is an application of Bayes' rule, which is this. So we have, which is written here and a few other places on this. So the learning scenario is that there's a collection of hypotheses. As we'll see today, hypothesis can be defined many ways. It can be defined as a class of functions. This could be your set of hypotheses, but it could also be a collection of parameters. This could be your set of hypotheses. And the goal is to find the most probable hypothesis. And again, under a general notion of what an hypothesis is. We call this maximum a posteriori. And in order to compute it, this is the probability we want to compute, or in fact, this is what we want to argmax over. We want to find the maximum posteriori h, so we're going to try all h's in our class, find the argmax, and in order to compute this, we're using Bayes' rule that says you can compute this by computing P of d given h, P of h, and in fact, you don't care about P of d. What these two mean is that you need to have a prior over the collection of h's, and you need to be able, given an h, to figure out what's the probability of observing this data. And we've already given a few examples for this, which I will not go over, but we'll go over a lot of other examples today. Okay, so this was the last example that we've done, and you will see it again in the problem set where we'll ask you to do, to completely solve it. And I want to give one other example, at least. And this is a famous example. It's called hidden Markov model. A lot of you have seen it, but I want to cast it in the same framework that we were talking about today. So again, what we have is we have a generative model. So we have some problem, and we have an idea of how to model, how to generate this data. In this case, the data that we care about consists of 5 characters, A, B, C, D, E. And we assume that there is also a notion of a state. In this case, we have 2 states, B and I. You can think about it as beginning. So assume that you have some sequence, and the sequence consists of 5 characters. And there is a special, each character could either be the beginning of an interesting event, or it could be inside an interesting event, right? So everything in the sequence belongs either to an I state or a B state. So in order to define the model, we need to understand how we're going to generate it. So first of all, we need to know something about the states. We have initial state probabilities. In this case, it's 0.5 for B, 0.5 for I. And the way we're thinking about this model is as follows. So you have this automaton. So you can be in a state, either B or I. If you're in a state B, you can either stay in state B with probability 0.8. This is the transition probability from B to B. Or you can move to another state. Similarly, if you're I, you can stay in I, or you can move back to B. In a given state, what you do is you emit a character. So if you're at B, you, with probability P of X given B, you emit one of these 5 characters. So these are the probabilities here. P of A if you're at B, P of B if you're at B, P of C if you're at B, and so on. And the same with I. If you're an I, you emit a character with these probabilities. I need here 5 different probabilities that sum to 1. And then I decide if I stay at I or I go to B. So that's the, and we can think about it also as a sequential process. So I'm starting somewhere. I can start either at B or at I, and this is the probability that determines where I start. And then I emit a character, and I move to another state. I meet a character, and I move to another state, and so on. So that's my generative model. Okay? So it's a slightly more general model or more complex model than the one that we've done last time, where we did not have this notion of states. We just had emit characters. But conceptually, it's the same thing. So what are the problems that we have here? It's really the same thing as before. We have a collection of observations. Observations in this case are the characters that we've produced and the states in which we produce them. Everything is observable. It's called hidden Markov model for a reason, but in my scenario here, nothing is hidden, right? We observe the x's and we observe the states. And our goal is to find the most likely parameters of the model, because eventually I want to be able to, given an unlabeled example, which is going to be just the characters that I've omitted, to predict the states. So you can think about it in the following way. Let's think about it as a part-of-speech tagging problem. So given a piece of text, let's say a sentence, eventually you want to be able to predict which part-of-speech tag each word appears in, whether it's a noun, an adjective, a verb, and so on. So in training, you're going to get the words x1 up to xm and the part-of-speech tags, which are the states. In test, given a sentence, our goal is going to be to predict the part-of-speech tags, right? So that's one example of this. How are we going to do it? If we know these parameters, right, so we know the probability, the initial probability of the states, we know the transition probabilities. What's the probability of moving from one state to another? In the power speech tagging example, this is the probability of a verb following a noun, a verb following an adjective, a verb following another verb, and so on. And the emission probabilities. What's the probability of emitting one of these characters given that you are in a specific state? In the power speech example, this will be, assume that you're in a noun state. What is the probability of emitting the word table, the word carpet, the word board? And all of them have some probability. None of them is 1, because table could be a verb also. But these are the probabilities. And then we want to estimate this. So how do we do it? Again, we're doing it using Bayes' rule. We want to do argmax over all possible labels. Notice that a label here for us is a sequence. It's a big label. But still it's a label. From the perspective of the theory that we had, nothing has changed. P of L given X is going to be computed as P of X given L. P of L divided by P of X. The only issue here is that it could be hard to compute. So P of L is basically consider all these labels that you've seen. If the sequence is of size 20, and let's even take the case that you have 2 states, there are 2 to the 20 different possible labels here. So this is P of L, and you also need to compute P of X given L. So you can see that there is a computational issue because there are a lot of numbers that you have to compute here, but that's a technical issue. From the perspective of the paradigm, we've solved it. Okay? So we're going to talk today about some solutions to this computational thing, but for now, I care more about that it's clear that we've solved the conceptual problem. Questions? Okay. So before we get to solving this computational problem, I want to highlight one thing. So how can we use this general paradigm that we have? Basically, the question is, what should H be? And as I said, we basically are using Bayes' rule, and we can instantiate H in many, many different ways. For example, H could be a collection of functions. Given training data, I'm going to choose a function. I'm going to choose the most probable function, the most likely function, or the most a posteriori function. And then, given new data, I'm going to use this function. That's option 1. There's another option. H could be a collection of predictions. Right? So given data, I'm going to do something to find the most likely prediction or the maximum posteriori prediction. And these two things could be different. So here's an example. So what do I do here? So in the first case, I'm learning a good function, a good hypothesis. And you know, there are many examples that we are doing it. And I'm using this HMAP, where H is a function. Could be a language model, could be a model for the HMM before, a collection of the parameters of the HMM. The second one would say, I don't really know what is the model that I'm using now. I'm going to go for the most likely decision, prediction. So really, if you think about it, it's an issue of thresholding, because even when you make a prediction, you are using some function to make the prediction, but you don't necessarily commit to the most likely function. You still keep the uncertainty, and you do the most likely at the level of the prediction. Here is an example of what I mean. So let's assume that I have in my class 3 hypotheses, H1, H2, H3. And these are the probabilities the posterior probabilities given the data. I already did some of the work here. 0.4, 0.3, 0.3. So the most maximum posteriori hypothesis here is H1. Now, given an example X, let's assume it so happens that H1 of X is 1 and H2 and H3 of X is 0. I've already committed to the maximum posteriori H, and therefore, what's going to be my prediction here? It's going to be 1 because I committed to this model. This is my function. So in this case, the H maximum posteriori of X is 1. However, I could say, forget this. Don't make a decision here. Instead, defer your decision and make the most probable prediction or classification by integrating all your hypotheses with their posterior probabilities and then make a decision. So really, what I'm going to do is this. Let's assume that V is the set of all possible classifications now. Now I'm being Bayesian about the predictions. So the probability, I'm looking for the probability of the prediction given the data. And what I'm doing here is I'm using the total probability formula. Another way of saying it, I'm marginalizing over all possible hypotheses. Before I committed to a hypothesis. Now I'm marginalizing over all these. Basically what I'm doing is this. I'm writing this as sum over all possible H's, P of V given H and D, times P of H given D. This is always true, right? This is just the total probability table. Notice, by the way, that I can simplify this a little bit, and instead of this term, I can write P of V given H. Why is that? Yeah. Yeah, so once I know H, I don't care about D. P of V given H is the same as P of V given H and D. V is independent of D given H, right? So I can write everything this way. And then if my prediction is going to be the argmax over all possible V's of this thing, P of V given D, which I've written already as sum over all possible hypotheses, P of V given H, P of H given D. Yeah. So it's not independence that matters here, it's conditional independence, right? So what I have here, I'm conditioning everything on D, right? So what I care about is, so you agree with this equality here? Okay, so now I'm replacing this. I'm claiming that P of V given H and D is the same as P of V given H. And the reason is that given that I know the hypothesis, the prediction is just evaluating this hypothesis. The data doesn't matter now. Right? So P of V is independent of the data once I'm given H. So P of V given H and D is equal to P of V given H. It's a conditional independent statement. Okay? Okay, so now that we agree with this, let's go back to this example that we had before. And now I'm not going to commit and say this is my maximum posteriori H, but rather I'm going to keep these values and given X, make the prediction directly on X. So what I'm going to do is I'm going to ask, what is P of V equal 1, right? This is what this notation means. What is the probability of predicting 1 given the data? It's the sum over all the hypotheses. The probability of predicting 1, given that I'm thinking it's HI, times the probability of HI given the data, which in this case is going to be 1 times 0.4 and 0 times 0.3 twice. And then I'm doing the same thing for the option of predicting 0. And what I'm getting is that the probability of predicting 0 given the data in this case is larger than the probability of predicting 1. Okay, so basically I was doing the Bayesian way in both cases, right? The important thing to remember here is that what I've done is I've been Bayesian about different things, or if you want to think about it, in a sequence of decisions, rather than making the Bayesian decision in step 1 and living with it, I've maintained the uncertainty and I made the decision later. Now, of course, this is going to cost you, right? Because in this case, it's very simple, but if you think about it, I had to carry with me this table, rather than just knowing, well, it's H1, live with it, and work with it, right? So this is a simple example, but hopefully the idea is clear here. So you can be Bayesian about multiple things. And the key example of where we are actually going directly for a prediction is this very important example of the naive Bayes algorithm. So naive Bayes algorithm, in some sense, is going back to the previous part of this class, where we just talk about classification. It's a classifier, as we will see. It works in a different way, at least seemingly different way, than the classifiers we've studied before, and we're going to talk about these differences. But it's a good classifier. So in fact, it's a surprisingly good classifier in practice. So you know perceptron, you know SVM. In many, many applications, it turns out that naive Bayes, that is much simpler in principle than these are, actually is working well. And we want also to discuss a little bit why is that the case, that it works so well. Yeah. So the range of hypotheses that we consider are the range of labels. So now I'm going to call the label, the possible labels, I'm going to call them hypotheses, and I'm going to apply the Bayes theory for choosing the most likely or the maximum posteriori label. So it's the same game as we did before. Instead of H, I'm going to call it L or V now. But it's really the same framework that we're using, as we will see in a second. Okay, so what do I want to do now? Now I have a function that maps X to V, a finite set of values. Instances basically are a collection of features, just like before. Let's assume now, for the next few examples, that it's Boolean, but we will change that. And given an example, I want to find the most probable value in V, right? So V is my H from before. I'm going to use Bayes' rule. So I'm going to try to find the maximum posteriori V, which is the argmax over all possible V's, P of Vj given X, which is the argmax over all V's, P of V given, this is just instantiating the vector. And let's use Bayes' rule. Bayes' rule is going to say, okay, so do P of X given V times P of V divided by P of X. For the sake of argmax, I don't care about it, so that's what I care about. So we, again, conceptually, we solve the problem. And okay, this is something that we've already done before, and I think you understand this. Just a reminder that whenever I say P of V or P of Y or P of X, I mean P of the variable equal taking this value. So P of Vj means the probability that the label takes the value Vj. Okay, so that's what we want to do. And given training data, we just want to estimate these parameters. So we have really two families or two types of parameters. We have this parameter, the probability of V, and the probability of X given V. So P of V, I have a finite set of labels, maybe a small set of labels. As we said before, if I'm assuming binomial distribution, for example, all I need to do is count the number of times V appears in the training data, right? So I have 7 labels. Out of 100 examples, I'm going to count how many times each label occurs, and I have P of V, right, under this binomial distribution. What about this? Do you see a problem here? Yeah?
Can you try to estimate that directly from the data?
Right, so probably there's a lot of instances. So these are our instances, our sentences, or feature vectors. We probably haven't seen many of them, right? So if we just try to estimate it this way, by counting, most of them will probably be 0. We get nothing. So we're going to make some assumptions. These assumptions really are the assumptions that are going to drive generalization here. Right? So we have to generalize. We cannot assume that we've seen all the data, otherwise learning is uninteresting. We're going to assume that we've seen some data, and this little bit of data that we've seen is going to allow us to generalize to things that we haven't seen. The question is, what assumption do we have to make, given that, clearly we cannot estimate it? As I said, most of these will never occur. So really, in order to do this, we have to make some assumptions, and the assumption that we're going to make is as follows. So first of all, let's just simplify it. So what I'm writing here is the probability of x1 up to xn. Remember, these are my features given Vj. I'm writing it as P of x1 given the rest. So basically, I've chosen an order over my features. The order I've chosen is first x1, then x2, then x3, up to xn. Given this order, I'm saying that P of x1 up to xn given Vj can be written as P of x1 given the rest, comma Vj, times P of x2, xn, given Vj, right? This is always true. I didn't make any assumption here. I'm copying this, and I'm rewriting this again. I can write this as P of x2 given the rest, times P of the rest given Vj. Again, no assumption, right? This is always true, and I can keep on going until I'm going to have P of x1 given the rest, times P of x2 given the rest, and so on, times P of xn given Vj. And again, this is no assumption here. Now I'm introducing an assumption. And the assumption I'm going to make is that the feature values are independent given the target value. Given Vj, x1 is independent of x7. Once I do this, I can simplify it and write it this way. So x1 is independent of all of these given Vj, so I can just write this as P of x1 given Vj. Same thing for all of them. So that's my assumption, yeah?
I thought you have the assumption of...
Oh, we never assumed. It's a good question. So the question is, did we always have the assumption that features are independent and are IID? What did we assume in the PAC framework, in the first part of the class, is IID? The examples are IID. So when I see, I sample examples from one probability distribution. We didn't know which one, but it's one fixed probability distribution. And examples were independent of each other. I made no assumption whatsoever about the features. It could be that all the features were the same, right? When you ran the perceptron, in fact, in the problem sets, in many of the cases that you ran, the features were identical, right? We kind of constructed them this way, right? If you think about the problem set that you did on Wino, Perceptron, and Adagrad, the way we generated data, a lot of the features were identical, right? That didn't bother us at all. So features, we know nothing about the features in general. The examples are independent, independently sampled, and we're going to assume that throughout. There's very little we can do without using, heavy machinery if we don't make this assumption. Now, let me just say, given this question, in practice, you could argue that it's completely wrong to assume that examples are independent from each other. Because, the scenario is such that if you observe this example, you're a lot more likely to observe this example than something else, Nevertheless, it's not a bad assumption in most cases. So relaxing it is technically hard and doesn't give a lot. But here it's a completely different assumption, right? So here I'm assuming something about features which we never assumed before. Was a question? Okay. So basically this is the assumption that we had now, right? So we assume that because the feature values are independent given the target value, we can write this. I'm basically writing everything with more details. The probability that the first feature is V1, the second feature is V2, given the value is Vj, as the product of xi, the ith feature or the nth feature is Vn, given this. That means that now the parameters that I need to estimate are these things. And I omitted in this case this one. So this also tells me, yes? Okay, excellent question. So the question is, what happens when I blow up the feature space? So your intuition is that if I could assume that things are conditionally independent given the label for x1 up to xn, now that I'm looking at products of all pairs, it's definitely not true. Nevertheless, we're going to do this and keep this question because I'm going to get to it at the end, I hope. Yeah. Okay, so this was the Bayes rule that we used, right? So we started by this. This is our hypothesis, V, P of V given X. We used Bayes rules to move it to P of X given V. Because X is a collection of features. Yeah, so this is a data point. X1 up to Xn is a data point. And now we take the data point and decompose it to a collection of features. Okay, so we made two steps. One step is from P of V given X to P of X given V, using Bayes rule. And the second one is via our assumption here from P of X given V to P of Xi given V. Okay, two steps. So let me just continue with this for a second. So think about, again, it's a generative model, just like we said last time. Basically, our model assumes that we are generating the data in a specific way. How do we generate the data in this way? We first choose the label according to the probability P of V. Once we have the label, we are choosing the features x1 up to xn according to this probability distribution. So again, it's a generative model. You can think about it as a tree. I'm going to show it as a tree a little bit later. So just to summarize, we need to estimate P of V, and we need to estimate for each xi, P of xi given V. So P of V is size of V parameters. Well, in fact, this minus 1, because I know that they sum to 1. And for each value of V, I have to estimate n parameters, P of xy given V. Again, minus 1 in each time, because they have to sum to 1. And the only question now is a technical question, how to estimate it. But we basically know how to do it. So here's an important point, though. So notice that it's a very, very different learning algorithm than before. Before, the learning algorithms that we had were mistake-driven or error-driven, let's say, right? So we actually did search. We did something. We looked at how well we were doing. Are we consistent? Not yet. Let's change something. Here, it's a one-time computation. Here is the data. Look at it. Compute something. And you have the hypothesis. You have your function, right? So it's really no search and no attempt to achieve consistency or even approximate consistency, right? So this is very, very important, and it brings up the question of why does it work? I mean, before we gave explanation. What's the reason now that we could expect this to work? But what's the key assumption that underlies what you said? Why should it work? How did we develop it? How did we derive that these are the parameters to estimate? We made an assumption, right? We made an assumption that the probability distribution that generates the data has a property of conditionally independent. So under this assumption, it's not only going to work, it's perfect. You know, we are choosing the most likely hypothesis, right? It's the right thing to do. Now, of course, the question is going to be, well, this assumption is probably not going to hold, so why does it work then? And that's going to be an interesting question. But under this assumption, there's no surprise that it works. It's the right thing to do. Now, you will see in the literature a lot of time questioning of why does naive Bayes work, given that clearly the assumption is wrong. Or people say, I don't believe it's going to work because the assumption doesn't hold. And I'll try to argue later today that actually it's a pretty robust algorithm for reasons that we already know from the first part of the class. But let's just get to it in a second. So far, that's the assumption. Okay, so I want to just say one thing, kind of technical thing, because there is an issue of conditional independence and independence. And I want to just make sure that you understand that these are not the same thing. So I'm not saying that the features are independent. I'm saying that the features are independent condition on the label. These are very different assumptions. In fact, they are not weaker or stronger, they're just different. And I'm giving here two examples to illustrate that. I mean, these are kind of invented examples, but still they will illustrate it. So basically, I'm giving an example from a Boolean domain. I have two features, x and y, and I have a function, or a label if you want, L. And in this example, the label is simply the conjunction of x and y. And I'm defining a probability distribution. In this case, the probability distribution is going to be the product distribution over the uniform distribution. So I'm assuming that x is 0 or 1 with probability half-half. Y is 0 or 1, probability half-half. And then I'm defining a distribution as a product distribution. which essentially means I'm defining them to be independent. I'm saying that the joint probability P of xy is P of x times P of y. By definition, that means independent, right? And indeed, if you check, you will get this, right? So this is the truth table, if you want. So it's 0, 0 is probability quarter, 1, 1 is probability quarter, and so on. Now, if you check now, so here x and y are independent. If you just check the conditional case, let's assume that L is 0. The label is 0. Look at this table. L is 0 in these 3 cells. So it's very easy to see that given that L is 0, x and y are not independent. Because the probability of x being 1 when L is 0 is a third. The probability that y is 1 given that L is 0 is also a third. But the probability that both of them are 1 given that L is 0 is 0. So they are not conditionally independent. So this is one direction. I can also give an example in the other direction. All right, so we will take a case, we will build a case where x and y are conditionally independent, but they are not independent. So in order to do this, we are going to define the following distribution. I'm going to define, in the case L equals 0, I'm going to say that the probability that x is always 1 and y is always 0. And in the case L equal 1, I'm saying that x is always 0. Probability of it being 1 is 0, and y is always 1. So basically, this is the table I have now. And now, if you look at it, I defined it so that, and also I'm assuming that the label is uniform, either 0 or 1 with probability half. Now, it's easy to check that given any value of L, they are independent. I define them to be independent. You'll see that the product is 0 all the time. However, x and y are not independent. And again, you can compute it yourself. Here is an example. P of x being 1 can be written as P of x being 1 given that L is 0 times P of L is 0, plus P of x being 1 given L is 1 times P of L is 1. You will see that it's 0.5. The same thing if you do it for y, it turns out to be 0.5. However, the probability that both of them are 1 is 0. They are never 1 together. Anyhow, so these 2 examples are simple examples. You can verify it for yourself. The message that I want to make sure you get is that these 2 are 2 different notions. So we are not assuming here that the features are independent. We're just assuming that if you know the label, they're independent. Okay, so now let's go back to naive Bayes and just run through an example quickly. So here is the data set that you've already seen before. We've played with it. So again, I have 4 features. I have some labels. And in this case, I want to predict using the naive Bayes algorithm. Again, that means I'm going to estimate P of V, and I'm going to estimate, given each V, P of xi given V. How do we do it? We already talked about how to estimate this. Basically, I'm going to split my screen to 2 sides. On one side, I'm looking at the probability of yes. On the other side, I'm looking at the probability of no. And in each side, I'm looking at all xi's given yes. On the other side, all the xi given no. Very simple. So the only thing I want you to make sure is that I have a lot of numbers here, right? So P of outlook given equal sunny, rainy, 3 numbers here, 3 numbers here, and so on. I have a lot of numbers, and I have to compute all these numbers in the learning time. Now, given an instance, actually, I'm not going to use most of these numbers, right? What will I do when I get an instance? I'm going to say, oh, okay, you care about outlook sunny. So we're going to go to here, take the outlook sunny given yes and the outlook sunny given no, and grab these 2. You want temperature cool, so I'm going to go to temperature cool given yes and given no, take these two numbers and so on. And again, I'm going to build two products. Product of the xi given the yes, and on the other side of the screen, product of the xi given no, and it will look like this. These are the four numbers I'm going to plug into my yes side. These are the things that are in my no side. All the other parameters that I've learned, I don't care about for the sake of this instance, right? And I'm just computing the product. So in this case, I know it must be this. It's no. And notice also that all I care about is the relative order of these numbers, right? I'm doing argmax. I could compute the probability. This basically amounts to normalizing it. So the probability of no is actually this, but we don't need to do it in order to make a decision. Simple algorithm. Now, a question. What if we were asked about outlook equal overcast? So of course, you may not remember. So remember the question, and let's go back to the data. What if I'm asked about outlook being overcast? What do you see? It's always yes. What does this mean? That in all four cases it's yes. So basically, instead of sunny, I will put overcast. Here, instead of sunny, I'll put overcast. Here, I will get 0. What does that mean? The product is also going to be 0. But in general, what does it mean about the naive Bayes algorithm? But in general, what can you say? Yeah? Okay, before we are adding anything and correcting the algorithm, which we're going to do in a second, you can say something. Yes?
If you don't see all the possibilities, the ones you don't see.
So if you haven't seen one of the features in an instance that you want to predict on, this instance will have probability 0. You will never predict what you haven't seen for it, right? Because this is going to dominate the product. So if you haven't seen one of the feature values as a yes example, you will never say yes on an example that contains this feature value, and vice versa for the no. So the 0 dominates here. Of course, you don't want this. You want to do something, but it's important to realize. So, okay, so of course, when we estimate parameters, we want to correct for that. So the simple way that we suggested before is under the binomial assumption, all we do is this, right? So the probability of something given V is the number of times this something happens divided by the number of things that happen, which is this. Again, I want to remind you that this is under a specific assumption, right? So I could have made another distributional assumption, and this formula will not be right. And you'll see it in the problem set, right? We can change the distribution. You'll get a different way to estimate. But binomial makes sense in these cases, so let's just keep it. So as you already realized, sparsity is a problem here. If n is small, this estimate is not correct. And if nk is 0, it will just dominate the estimate. So these two problems occur, and we have to do something with it. So this process is called smoothing. Basically, we want to smooth the estimates away from 0. There are many, many ways to do it. The ways to do it often depend on the model that you're using. If you're using naive Bayes with binomial, you would do it in a simple way. And it turns out that, really a lot of simple ways are equivalent. Some better justified than others. if you're dealing with other models, perhaps you want to smooth in a different way, but smoothing is really important. So in this specific way, one way to smooth it, and in fact, let me go back to the next slide because it simplifies it, is something that is called the Laplace rule. So in the Boolean case, what I'm going to assume is that I'm going to just do nk plus 1, so the number of occurrences that I observe plus 1, divided by the total population by 2. So essentially, what I've done is I prevented zeros here. I will never have 0 in the numerator. And I also push the denominator away from 2. So from a small number, I'm increasing it a little bit. Now, why does it make sense? So as I said, a lot of smoothing are really hacks or hand waving. It turns out that this one actually can be explained somehow. And I'm going to show how to explain it, mostly because this explanation introduces some important concept that you should know about. So how do I make my estimation a little bit more robust? So remember that we are talking about this binomial random variable, and the probability of observing k out of n tosses when the parameter is theta, the head parameter, if you want, is theta, is this. And we used this before in order to determine the most likely value of theta. We did it last time. We figured out that it's k over n, right? So the number of heads divided by the sum of these two. P and k is n choose k. Now, this is the probability. Really, for the likelihood, it doesn't matter. The C and K is a constant. It doesn't matter for the likelihood, but just for completeness, it's here. Now, let's assume instead of, so before we did not assume any prior. We just cared about the maximum likelihood. If I want to assume priors, if I want to do the map, maximum posteriori estimate, I need to assume a prior. Which prior should we assume? So what's commonly done is to assume a prior that has the same form as the posterior. So in this case, I'm going to assume a prior that also look like theta to the something, 1 minus theta to the something. And the notation is going to be theta to the a minus 1, 1 minus theta to the b minus 1. And the reason is that if I choose a and b to be 1, I'm getting a uniform prior, right? So I get 1 there. So this prior is called, so this is the beta distribution. You might have seen this before. The important thing is that because I'm assuming it in this form, what I get is that the posterior is also the same form as the prior, as you'll see in a second. So if you compute the posterior, which I did here somewhere, okay. Sorry about you see all the secrets now because of this animation. Let's compute first the posterior here. The probability of theta given d is basically the probability p of d given theta, Bayes rule, times p of p theta. P of d given theta is just this thing. With k and with n minus k. And the prior is the same form with a minus 1 and b minus 1. So what you get is that the posterior is theta to some power, 1 minus theta to some power, and the powers are just the sums of what we get. So it's a plus k minus 1, b plus n minus k minus 1. Or b minus 1 plus n minus k. So essentially what I got by choosing this prior is that the prior and the posterior have the same form. And this selection of prior is called conjugate prior. Just the idea that I get the same form, because of that it deserves a name. And you will see a lot of times when you're looking at a specific probability distribution, you're you're asking, okay, so what's the conjugate of this probability distribution? And the question basically means which is the right prior to choose so that the posterior looks the same as the same functional form as the prior. Okay, so basically, let's eliminate this again. Okay, let's just do it. So now, because I have this posterior, we can compute the maximum posteriori parameter. It's exactly the same thing that we did when we started with this. We got the maximum likelihood. And the way we did it, if you remember, we took the log, and then we differentiated. And we said, let's assume it's equal to 0. We solve, we got k over n. In exactly the same way, if you just take this now, you take the log, you differentiate, what you will get is you will get, again, this coefficient divided by the sum. Just like here, we got k divided by the sum of these two. So in this case, what you will get is that maximum posteriori theta is k plus a minus 1 divided by n plus a plus b minus 2. Now, as a sanity check, let's substitute a equal b equal 1. We know from here that a equal b equal 1 gives us the uniform prior, which means that we should go back to the maximum likelihood. And indeed, if you substitute here a equal b equal 1, you get back to k over n. So, makes sense. Now, why is this important? It's important because now that you have this posterior, you can compute the mean of this posterior. What does it mean, the mean of this posterior? So basically, you have an experiment, right? So you toss a coin, k times, n times, and you get k heads. You can ask yourself, given a probability distribution, a prior that is something like this, what is my expected outcome given this? And it turns out that if you compute it, what does it mean to compute the expectation of theta? It's basically the integral of theta times p of theta given t, right? This is the posterior expectation by definition, right? Theta times p of theta given t. If you compute this, you will actually get this number, a plus k divided by a plus b plus n. That's the mean of the outcome, which basically means something very interesting. It means that when you run this experiment under this prior, let's plug in for sanity a equal 1 and b equal 1, the uniform. What we're going to get is we're going to get that the mean, posterior mean of observing kn, that is n tosses, I'm going to observe n, is this, k plus 1 over n plus 2. Which kind of is a justification for why I should smooth this way. So if I observed k heads in n experiments, I'm going to call this k plus 1 over n plus 2. So that's the justification for what is called the Laplace smoothing. And again, I just gave it to you under this specific prior, but this is the general case. If you want to assume a different prior, you will have the general formula. Okay, so again, this is just an explanation for one of the priors, but for one of the ways to do smoothing, which is this way to do smoothing, it's important to do. That's the key lesson here. Okay. So we are done with naive Bayes. It's a simple algorithm. But what I want to do now is I want to explain a little bit of why does it work. So the first observation is going to be, we're going to make it in the case of two classes. The same actually is going to happen in k classes. Notice that when we use naive Bayes, it essentially gives us a way to do prediction, right? Given x, naive Bayes tells you how to predict. How do you predict? you predict if the ratio between, you predict 1 if the ratio between these products is greater than 1. What is this product? Is the probability of V being 1 times the product over all features of x, y given 1, and the same thing for 0. Right? Nothing here. I just, instead of argmaxed, I wrote it as a ratio. Now I'm going to do the following trick. So I'm going to denote pi, p of xi being 1 given v, being 1, and qi, p of x being 1 given v equals 0. Right? So this is just a shortcut because I don't want to carry all this with me. And then I'm going to write this ratio in a slightly different way. And this is actually an important trick here. I already pointed this out last time. What does it mean? Remember that when we did the naive Bayes, we said, I'm going to compute a lot of parameters. A lot of parameters given yes, prediction is yes. A lot of parameters given prediction is no. But at decision time, I'm only taking a few of them, those that are active in my current example, right? Now, if I want to write something mathematically, I don't know which are going to be active. You're giving me an example. I don't know how to write this because I don't know which of the features are active. So the trick to write it is this, to write pi to the xi, 1 minus pi to the 1 minus xi, right? So I don't know whether in the ith coordinate I should put pi or 1 minus pi, because I didn't look at the example. I don't know is it on or off here. So I'm writing it this way. Notice that if xi is 1, it means that I'm counting pi, and this becomes 1. If on the other hand xi is 0, I'm putting x minus pi, 1 minus pi into the product, and this disappears. It's 1. Okay? So this is a compact way to write what the naive Bayes is going to give you without knowing ahead of time what is the example. So this is just a substitution of this, just an algebraic trick. Now I'm going to rewrite it by dividing everything, denominator and numerator, by 1 minus pi, or taking 1 minus pi outside the parentheses here. So I'm getting pi over 1 minus pi to the xi. Check again that what I have here is 1 minus pi to the 1 minus xi. And pi is still to the power of xi, right? So I did nothing. Same thing in the numerator. Now I take a logarithm of this, and this is what I get. So I have a constant here. I don't care about this constant. It comes here. Plus, I have another constant that comes from taking this log, because this is power of 1. So it's the log of 1 minus pi divided by 1 minus qi. And these components, when I take log, give me a linear sum of log of this minus log of this, all multiplied by xi. What is this? What did I get here when I took log of this ratio? This is a specific type of function, and I'm saying I'm going to predict 1 if and only if this specific function is positive. But you've seen this function before. What is it? It's a linear function, right? So basically I have here some coefficient. You can call it b if you like. And I have here a dot product between a vector of numbers and my features. So this is really a linear function. And I'm saying if this linear function is positive, say 1, otherwise say 0. So essentially what I've shown is that with these as coefficients and some constant, this is a linear function. So really naive Bayes makes a decision using a linear separator where the coefficients are very specific numbers computed from the probability, right? So really we're playing a very, very similar game to what we've played before, only that we learn the coefficients in a very, very different way. right? We learn it by estimating some probabilities from the whole data that we've seen. So now you can rewrite it in another way. So basically, what we've seen now is that this decision, the log of this ratio, can be written this way for some specific wi's and specific b. I can also write it, just because it's interesting, since I'm dealing with the Boolean case, I can write P of v being 1 given x is 1 minus P v being 0 given x. So doing some algebra, which I'm writing here, you can get that the probability of v being 1 given x is 1 over 1 plus e to the minus this linear function. We've actually seen this function before when we talked about perceptron and so on. So this is just another way to write it. But the key lesson is, so far, is that what we've shown is that naive Bayes makes its decision using a linear function with very specific ways of computing the coefficients. Yeah? Okay, so I wouldn't say, so the question, is it a special case of support vector machine? I wouldn't say it's a special case of support vector machine. So we've talked about a range of algorithms, all of them making linear decisions, and this is one of them. In all cases, the coefficients were derived different ways. In perceptron, they were derived one way. In undergrad, they were derived another way. In Wino, another way. In SVM, another way. Each time we justified why we derive it this way. Here, all I'm saying is that forget independence assumption, forget anything. This is how you make the decision. It's a linear function. Now, in the homework, you will see that it's actually a restricted type of linear function in the following sense. There exist some linear functions that you cannot express using naive Bayes. So again, I'm not going to give you the details now. You'll read the problem set and you'll see. So it doesn't have full expressivity in this sense, but it is a linear function. So really, the linearity of naive Bayes provides a better explanation for why it works than what we've said so far. So given that all I have is 2 minutes, according to this, so let me kind of run through an explanation of why it works. So basically, all I want to convince you, given that you are experts in learning theory now, is that the real explanation of why it works is what we've said before, learning theory. So okay, this is just repeating what the slide that I had before. This is a graphical representation of what we had, right? So we had a label, and given a label, we had a lot of features. I'm calling the features now chi-i, because I actually don't care what are the features. I'm going back to your questions from the beginning. What happens if I don't have just xi's, but some functions of the xi's? So basically, what I've said is that, forget this, this is actually what we've done before, is that the prediction of, with respect to x, of naive Bayes is done by doing some argmax over a linear function, where these coefficients are computed as a ratio of probabilities. That's what we've shown before, and this is shown here again. What does this mean? So now notice that it doesn't matter what the xi's here are. There could be just x1 up to xn. There could be some function of the xy. Independent of what you choose the features to be, this is how naive Bayes is going to make the decision. Now, basically, and this is a well-known sort of family of function that is called linear statistical queries model, and it has some nice properties. Okay, I don't have time to talk about this. Basically, these slides are saying that the same thing we said about naive Bayes could be said also about, okay, Doesn't work, so let's go back to this. The same thing I said about naive Bayes can be said about hidden Markov models, and I'm not going to show it here. Basically, if you look at the slides, you will see that I'm claiming here that the same thing, hidden Markov models make decisions in a linear way. It's basically argmax over some linear function. The coefficients are computed somewhat differently, but still they are ratios of probabilities. What does it say? It goes back to what we've said earlier in the class. It says that we have low expressive functions. And therefore, independent of the independence assumptions, if you manage to explain your data, to feed the data with a low expressive power, it's a low expressive model, it's going to work. And really, in practice, what people are doing, they are not using this model, right? So they are actually replace, if they see that naive Bayes isn't working well, people are going to add features. People are going to blow up the feature space. And check again, is my naive Bayes working better now? Now, as you pointed out, when I augment the feature space by blowing up the feature space, if before I did not satisfy the conditional independence assumption, definitely I'm not satisfying it now. It's even worse. Nevertheless, my chances of fitting the data are higher now because I'm more expressive, and therefore learning theory says you're going to do better. So the real explanation is really this one. It's the low expressivity. And the same thing happens with HMMs. Again, people want to explain their data with an HMM. If it's not going to work, they're going to learn a more expressive HMM. They're going to add some expressivity. And the real explanation is at the end that you really follow the learning theory protocol. You try to learn a hypothesis that is consistent with the data. If you don't manage to, you make it more expressive until it fits the data. And then the low expressivity of the function class really explains it. OK, so we're going to revisit this a little bit next week. I just wanted you to get closure with this and understand it. So, OK. Chase, one second. I may not be able to talk because something